Hello class, these are our Calc AB notes for section 2.5, implicit differentiation. So up until now we've been working with explicit forms of equations. So an explicit form is y equals, and those are really nice to work with. An example would be like y equals 3x squared minus 5. So those are easy. We find y prime, we take our derivative, we're good to go. So implicit form is when we can't, I don't know why that's going to be the word can't. It almost looks like a T. It is a D there. Where we can't make y equal easily. Okay? So an example of that would be like an equation for a circle. Like x squared plus y squared equals 25, something like that. Where if I'm going to solve for y, I have to subtract x squared, I have to take a square root. It's a little bit more messy, right? Then I would have two things I have to worry about. I'd have a square root with stuff inside it. So the implicit form is really more useful, right? When I'm looking at implicit, I see a circle. It's easy to work with. So implicit differentiation So we can use that on an equation like x squared plus y squared equals 25, where the y isn't by itself. So it allows us to find derivatives of things that are not functions. Because let's face it, a circle is not a function. It does not pass the vertical line test. And you're going to find lots of other really creative looking equations that you probably never imagined before that are similarly not functions. So it allows us to take derivatives of lots of stuff. So let's remember, and this is kind of the nuts and bolts of how this is going to work. If I am taking my derivative of x, that's just going to be 1. Okay, and a lot of students kind of think of it as almost like they think of a multiplying problem, like d dx times x, and so they think of this like as dx over dx. Oh, that's just 1, right? And that's not exactly correct, but it works. It helps you kind of reason through it. The other thing that we want to remember is if we take a derivative with respect to x of y, all that we get is dy dx, and that's what we've been doing. Right? When we have these equations that are y equals and we take a derivative of it, it becomes dy dx. So we've been doing that kind of all along. And you could think something similar here. You could think of this as y over 1, and it's just making dy over dx. So you could do that same kind of like multiplying, thinking about fractions kind of logic. And again, it's not exactly correct, but it kind of can help you reason through this. It works in the context of like fractions and how fractions would work. So if I'm taking a derivative with respect to x of x cubed, it's just going to be 3x squared. That's it. Even if you decided to do chain rule and you multiplied by the derivative of x, it's just 1. So it's just 3x squared. So when I do my derivative with respect to x of y cubed, I get 3y squared, and then I have a dy dx. So I've had students tell me before that the y squared times the y kind of makes the y cubed to them. And so like this extra y is becoming the dy dx. But basically anytime I'm taking a derivative with respect to y, after I take my derivative, I have dy dx there. So let's do the next one. First, I'm going to distribute derivative with respect to x of x plus derivative with respect to x of 3y. This is not a necessary step. We're just trying to kind of understand how this works. So derivative with respect to x of x is just a 1. And then over here, I'm going to get 3 dy dx. So 3 times the derivative of whatever y is with respect to x. Okay, last one, because I have x times y squared. It's really like a product rule now. So I've got to do, like this is my f, this is my g. I'm going to do fg prime plus gf prime. So fg prime. So that means first I'm going to keep my x and I'm going to take my derivative of y. Well, that's going to be 2y, but because it's y, I have a dy dx. Plus, then I'm going to keep my y squared times my derivative of x, which is just a 1, and then I'm going to kind of simplify this. So I have 2xy dy dx plus y squared. So I really kind of like this dy dx, this kind of notation for this, because of the stuff I wrote in purple here and how students kind of reason through that. But I could also use my like y prime notation. And the way I would do that, well, 3x squared is just going to be the same. This second one here, b, would be 3y squared y prime. My derivative of y is just y prime. This one would be 1 plus 3 y prime. The last one would be 2xy y prime plus y squared. I typically kind of avoid this in AB just because I worry that students will try to multiply y times y prime. And I do feel like this dx over dx makes 1, dx of y is dy over dx. It just kind of makes sense to students. But I don't care which notation you use, and I'm perfectly okay with both of them because the y prime is a lot faster. So basically, anytime we take a derivative of x, we're good to go. Anytime we take a derivative of y, we follow our derivative rules. We also add on the y prime, or the dy dx. So we're going to go ahead and we're going to take a derivative with respect to x of this whole thing. There's x's and y's mixed together. So basically, our steps are to first, I'm going to do steps over here. First, take a derivative or differentiate with respect to x. And I didn't mean to write that. I wrote it like a variable t. So with respect to x. So that means d dx, right, on everything. The second thing that we're going to do is we're going to move it around and we're going to isolate either that y prime or dy dx, whatever notation we want to use. I'm going to do the first one with dy dx notation, the second one with the y prime notation. So these are our steps. So first I'm going to go through and I'm going to take my derivative of each part. And you could go through and you could write d dx of y cubed, right, plus d dx of y squared. You do not have to do this step. Minus d dx of 5y minus d dx of x squared equals d dx of negative 4. So first I could say like, hey, I'm going to take the derivative of everything. I'm doing it on both sides of the equation. All right, and then the first one I have a y. So I know power rule 3y squared, but because it's a y, I'm going to also write dy dx. Plus, second one is also a y. So when I take my derivative, I follow my power rule 2y, but I also have dy dx. Minus. Next one, derivative of 5y. So follow my derivative rules. Derivative of 5y is just 5. And then because it's y, I have dy dx. Minus, next one's an x. So derivative of x squared is 2x. The d dx, like that's gone, right? I was taking a derivative with respect to x, so that one's all set. And then on the other side, derivative of a constant is always 0. So basically, I want to isolate my dy dx. So I'm going to do that now by moving everything that doesn't have a dy dx to the other side of the equation. So I'm going to have a 2x over here on the right now. I'm going to add that on both sides. And then with what's left on the left, so I would have like these three terms on the left, and I'm going to factor dy dx out of all of them. So I'm going to have dy dx, and I did not mean to change color, so I'm going to change back, times, in parentheses, 3y squared plus 2y minus 5. All right, now I want to isolate dy dx by dividing on both sides. So dy dx is going to equal 2x over 3y squared plus 2y minus 5. All right, looks great. So one thing I want to point out, because students that are really confused, like why are we, I'll point it out on the next one. Never mind, let's do the next one first. So the next one we're looking at x squared plus 4y squared equals 4. We want to find the slope of the tangent line to the graph. So slope of the tangent line means I just need to take a derivative. My slope is the derivative. Slope is the derivative at a point, right? And then I'm going to write an equation for a line. I'll do y minus y1 equals mx minus x1. So these are kind of my steps here. So first I'm going to take a derivative, and I want you to think about, I'm going to use y prime notation this time. So I'm going to try y prime notation. And I know there's going to be students that say like, well, why do I have to make it dy dy dx or y prime. Like, why do I have to do that with y and not with x? So I want to think about how before, when you wrote something like y equals 4x squared plus 3x, what we were writing is we were writing dy dx equals, and then we were writing like 8x plus 3. So when I had a y here, I replaced it with dy dx. So the derivative of y, if I'm thinking about my power rule stuff, right? It's first power, bring it to the front, raise it to the 0 power. It's just a 1, but I'm writing dy dx. I'm not just writing a 1. It's way different than how I'm treating this 3x over here, right? So I've really, all the time, this whole time I've been doing math, when I have a y and I take a derivative, I've been writing dy dx. So it's not really anything different, okay? We're just having the y's mixed in with the x's now. So we didn't really think about it before. All right, let's go ahead and erase this extra stuff here. Okay, so let's go ahead and take our derivative. Same rules again. X squared, that's going to be power rule. I'm just going to write down a 2x plus 4y squared. Power rule, but it's a y. So I have to have like a dy dx or a y prime in there. So it's going to be 2 times 4, so I have 8y. Now it's the first power, and then I could write dy dx, or I could write y prime. That's what dy dx really means. Equals, derivative of 4 is just 0. So this is definitely a lot easier. It's a lot faster to write, but the y and the y prime are not the same. We cannot make them like y squared or something, and that's my concern. So I'm going to go ahead and subtract 2x on both sides. And then I'm going to divide both sides by 8y. And then I am going to go ahead and simplify it. So y prime is going to be negative x over 4y. So that's an equation, or not an, it's an equation, but it's really like that's my slope, right? That's my slope of the tangent line I could find by doing negative x over 4y. So often, like when we've had these kind of problems before, they give you an xy ordered pair, but we never really needed the y. Now this time we actually need the y. So m equals my derivative. And my derivative is negative x. Well, x is root 2, so negative root 2 all over 4 times y, which is 4 times negative 1 over root 2. So let's just simplify this. It's going to be a negative over negative, so I'm going to just ignore that part. When I multiply the 4 times 1 over root 2, it's just 4 over root 2. So let's remember that this really means root 2 divided by 4 over root 2, which is going to be root 2 times root 2 over 4, okay? I could also get this by doing my little, I'll show you my fancy fraction trick again that I really like. So root 2 times root 2 is 2. 4 is in my denominator, right? This is over 1, so it's just over 4. So I have 1/2. The other trick I could have used to simplify this that I think is faster is I could say root 2 is a baby denominator. Multiply the top and the bottom by root 2. Here it cancels. Here it makes square root of 2 times square root of 2 over 4. I would have gotten my answer much faster. So I really do think that multiplying by the baby denominators is a cool way to do these. All right, now that I have my slope, I need to write my equation for my tangent line. So let's see, I've got my x1, y1, I've got my m, I'm ready to go. So y minus my y1, so that's going to be y plus the 1 over root 2 equals 1/2 x minus root 2. And then what you're often going to see in, I did have to do slope of the tangent line, just double checking here. What I often see with calculus stuff is that when we write equations, we're going to do them almost in point slope, but we're going to solve for y. So the last step would be y equals 1/2 times x minus root 2, and then just minus 1 over root 2. And I know that that looks kind of ugly, but we're really kind of happy with it like that. We're just going to leave it. And they're easy to write that way. But I did write an equation with y by itself. Okay, next one, we are doing a second derivative. Depending on the copy of the notes you got, this problem might not be in here. You might have to like cross out your problem and write it in. This has changed a lot over the years, and so I feel like we might all have different versions, but this is one I really, really like because it's a second derivative, and that's cool to do on this. So I'm going to go through, I think I'm going to use my y prime notation again this time. So let's go ahead and do that. So when I take a derivative of x squared, it's 2x. Plus derivative of y is 2y, but because it's a y, I have to have a y prime in there, equals derivative of 25 is just 0. So now we solve for y prime. So 2y prime equals negative 2x. Divide both sides by 2y. And I end up with y prime equals negative x over y. All right, now we're going to go ahead and do a second derivative. So to find a second derivative, I have a quotient rule. And I'm going to have to make sure that when I'm doing my quotient rule, I don't forget about derivative of y is going to be the y prime thing, right? So I've got to do that. All right, so let's go ahead. We've got to do low d high. So, and I think I'm going to put the negative out in front of everything. I feel like that would make my life easier. We'll see. So low d high. So low is y. Derivative of my x is just 1 minus high d low. So high is x. Remember my minus sign's out in front, so I'm just going to pretend that negative's not there. So high d low. Derivative of my low, derivative of y is dy dx, or just y prime. All over low squared, that's going to be y squared. So let's go ahead and simplify this out a little bit. So negative, and then I have y minus xy prime all over y squared. And now we're going to do something really cool. So this y prime, I can actually make a substitution. Substitute. And I can substitute my expression up here. This is y prime. So instead of y prime, I can write negative x over y because that's equal to y prime. All right, so let's go ahead and do that. So equals negative of y minus x times negative x over y all over y squared. You really need parentheses around the top, but it's not incorrect. I'm over the whole thing. So this gives me a negative of y plus x squared over y all over y squared. All right, and then baby denominator again, right? So whenever I have that, I want to multiply by the, I have a complex fraction, so I'm going to multiply by the baby denominator. That's what I meant to say. I'm going to just recopy it up here. I know I didn't really have enough space for this before, so I'm trying to cram it in, but I don't know if it's getting better. So let's go ahead and we're going to multiply by y in the top and bottom because that is my baby denominator. When I distribute the y over here, I'm going to have a y squared. When I distribute the y over here, it's going to cancel the denominator. So I'm going to have negative of y squared plus x squared. My denominator is now going to be y cubed. So now I can do something else that's really, really cool. And I'm going to look at that y squared plus x squared, and I'm going to make a substitution. So if I go back to my original equation says, so OG, original equation, my original says x squared plus y squared equals 25. So where I see x squared plus y squared, I can go ahead and substitute 25. So now I'm going to have negative 25 all over y to the third power. And that is my second derivative. I actually could totally have moved this over and had more space. I think this is really cool because of all the substitutions. I wanted to make sure that we got to do one of those together. So for our last problem, try to do another tangent line. I've got another equation with x's and y's kind of all mixed together. They're hard to tease apart. So we're going to go ahead and just take a derivative and use implicit differentiation. I'm thinking though that rather than do product rule, I just might like multiply this out right now. So if I go ahead and multiply out my equation, my original equation would be x to the fourth power plus x squared y squared equals y squared. So let's go ahead and take a derivative. I think I'm going to do dy dx this time. I'm just trying to change it up. So this is 4x cubed. When I have x's, I don't worry. Okay, now we've got product rule. So I've got x squared and y squared being multiplied, and with y squared, we can't forget about our dy dx in there. So I take my first function, derivative of my second would be 2y, and then dy dx, plus second function, y squared, times derivative of the x squared, which is just a 2x, equals derivative of my y squared is 2y, but because it's a y, I have to have dy dx. Okay, so let's see. What do we need to do next? So now we need to just kind of clean this up a little bit. We want to get dy's and dx's, dy dx on one side, everything that doesn't have it on the other, but first I want to clean it up. So 4x cubed plus 2x squared y dy dx. I'm sorry, the dogs are terrible tonight. Plus 2xy squared equals 2y dy dx. Okay, so I'm going to subtract the 2y dy dx. Oh my goodness, Bucky. We really love him, but he's awful. He's very suspicious, and he sees his reflection in the mirror right now, in the glass. So now I want to, so I subtracted this one to move it. The 4x cubed and this one over here, those both didn't have the dy dx. I need to subtract those to the other side. So I'm going to have a negative 4x cubed and a minus 2xy squared. Okay, so all I did was move stuff around, subtract to move it, and then I want to factor out the dy dx. So that I have 2x squared y minus 2y. And my family's getting home. My house is about to get really loud. Okay, then I want to go ahead and divide on both sides. So my dy dx is going to equal, and let's go ahead and write down our fraction. We've got our negative 4x cubed minus 2xy squared all over 2xy minus 2y. So now I'm thinking what we should probably do is do some factoring, right? Because we have a mess right now. And I feel like if I factor some things out, I might even be able to reduce. I'm seeing I've got like a lot of 2's in there at least, right? So let's go ahead and factor out a negative 2 in the negative 2x in the numerator. I also think having things in a factored form is easier to work with. And then we have, let's see, 2x squared plus y squared. Okay. In my denominator, I'm going to factor out 2y. And I have, let's see, I feel like something happened here. Yep, when my family got home, I lost a square. So what I'm noticing is I have an x squared right here, and I didn't copy that through. So let's go ahead and add the x squared, add the x squared. So now I have an x squared minus 1. I knew I was supposed to have an x squared. The 2 on the top and bottom I'm going to cross out because they're factors. So now I have negative x times 2x squared plus y squared all over y times x squared minus 1. So now I've got to remember what my original point was, and that was to find the equation, find the tangent line to the graph. So now I've got a point. I've got an xy. I need to find a slope. So my derivative is my expression for slope. So let's go ahead and make some substitutions. So negative x, so negative root 2 over 2. And then it says 2 times x squared, so 2 times root 2 over 2 squared. Plus y is also root 2 over 2 squared. Okay, all over in my denominator. It's nice that I'm just plugging in the same number for x and y. So root 2 over 2. Root 2 over 2 squared minus 1. All right, so I see a root 2 over 2 top and bottom. That's just gone. Let's see, when I take a root 2 over 2 and square it, I'm squaring the top, which just becomes 2. I square the bottom, which just becomes 4. So I'm going to have a negative of 2 times 2 fourths plus 2 fourths. In my denominator, let's see, that's going to be a 2 fourths minus 1. So 2 fourths is really 1/2, right? So 2 times a half is just 1. And so I really have just 1 plus 1/2. And then in the denominator, I have 1/2 minus 1, which is a negative 1/2. So again, negative on the top and bottom, gone. All right, so now I have a 3/2 over a 1/2. So you could think, well, 3/2 divided by 1/2 is really 3/2 times 2 over 1. Or you could say, hey, multiply the top and bottom by the baby denominator. That still works. I'm telling you, it's like the coolest trick. We're down to just 3. Once I have a slope of 3, now I can go ahead and write my equation again here. So I am completely out of space. I'm going to put it up at the top. What the heck? So y minus root 2 over 2 equals 3 times x minus root 2 over 2. And then I'm going to do my AP trick again here and get y by itself by just adding root 2 over 2, which kind of feels like we're cheating because I didn't have to simplify anything. All right, y is by itself. Okay, so lots of stuff going on here today. I feel like the algebra is becoming a lot more difficult. I mean, look at this problem. If I had really actually missed that square and I hadn't gone back and caught it, it would have wrecked the whole thing. So we've got to be really diligent and pay attention to detail with our algebra. Hopefully it makes sense why we have a y prime every time we take a derivative of y. If not, make sure you ask about that. And as always, if you need help, please let me know.